Hello everyone. So I'm Jiaxin. I'm from Intuitive AI Research. Today I collaborate with my collaborators, Sirui from Walmart Global Tech and Vector from Georgia Tech. We are so happy to get this paper accepted by WCV this year, and we want to present our recent work on the quantification of image reconstruction uncertainty without training data. So as we know, image reconstruction is very typical inverse problem in computer vision. So we often have the following issues. The inverse problem is U-post, and we may not have limited sparse measurement in real-world applications. And also the data is often noisy. So let me show you an example. This is tomography in biomedical and healthcare. So we would like to reconstruct images by using sensor data from X-ray, CT, or MRI. The traditional methods include direct image reconstruction and iterative reconstruction. So like in solving optimization with regularization. Recently, deep learning are widely used to learn the inverse problem. Another interesting example is the black hole images, which is a big news in 2019. The ring is actually reconstructed by solving inverse problem with a set of measurements from different places in the world. And the inverse problem are also play an important role in many scientific user facilities like electron microscopy and neutron scattering in some national labs. So inverse problem are well defined, and the classical approach is to formulate a mathematical optimization with regularization. So Bayesian approach is another good way to determine posterior probability of possible solutions and finally provide a maximum of a posterior estimation MAP. However, this kind of point estimate without any confidence and uncertainty information, it will mislead some decision making, specifically when the measurements are sparse and noisy. So Bayesian approach with MCMC is also very computational intractable and difficult to handle high-dimensional problems. With the development of AI and machine learning, many deep learning approaches are proposed, but these methods have other limitations. Either need a lot of number of data, for example, Bayesian deep learning, or only pursuing a unique inverse solution like feed-forward deep learning. Beyond that, variational methods seem like a good way to approximate the posterior, but it is intractable to select the distribution if the true posterior is too complex. To deal with these challenges, we develop a deep variational framework by using robust general models with variance reduction for solving inverse problem. So to fully search all possible solutions, we propose to parameterize the target images using a general model, which is used to learn unknown distribution. So an approximate posterior distribution can be obtained by minimizing the KL divergence between the generative distribution and the target posterior distribution. But the question is how to select the general model. So in this work, we introduced a novel probabilistic general model. The name is normal flow, so which can exactly learn the probability density of the target distribution. So this is achieved by using a chain of invertible transformation that follow the change of variable theory. And the normal flow models is simply trained by MLE with the loss shown here. Okay, so let me show how normal flow models work with the variational framework. From the KL loss, we can use the flow-based model to calculate the likelihood exactly by mapping the latent density to the target density. Then, by replacing the data likelihood and the prior terms by using data fidelity and the regularization function, we will define an optimization problem with a new loss function. So the loss function can be approximated by using a Monte Carlo methods, which draw random samples to estimate expectation. Note that the log, the pi z is the latent density, which is consistent Gaussian distribution, so has no effect on the loss. The log determinist term is an entropy term, which can increase the diversity and the exploration of the solutions. Finally, the flow-based model parameters are obtained by minimizing the loss function. And now we have derived the mathematical formulation like the loss function variation framework and discussed the several advantages of the flow-based models. However, flow-based models also have some limitations, that is the expressibility and the efficiency. So as we've shown before, the flow model consists of a set of invertible neural networks. It may hurt the expressibility, right? So in addition, the change of variable theorem need to calculate the Jacobian determinant, which is often computationally intensive. Therefore, designing the efficient architecture is also very necessary. More importantly, when flow-based model to approximate a complex posterior distribution, we may use a deeper neural network architect. However, increasing depths will probably bring additional challenges like overfitting instability and additional model uncertainties. To deal with these issues, we propose the robust generative flow, we call it RGF, which are based on neural spline flows. We also use bi-directional regularization to improve the stability and using gradient boosting to enhance the expressivity. More details can be found in our the paper. So once we learn the flow model, you may be curious how to generate samples efficiently. So commonly we may use simple random sampling in the latent space, but the variance is often high. So here, to reduce the variance, we propose to use non-hierarchical sampling to achieve significant variance reduction in both a latent space and a target space. And evaluate the generative model performance has been a challenge. Previously, we may use precision and recall as the metric, but recently two reliable metrics, density and coverage, are proposed by SML 2020. So we may use all of them to evaluate the performance of the generative samples from our proposed RGF model. So here's a combination of our RGF model with the straightforward baseline models in terms of the expressibility on toy images generation. So given the energy function, we show the generated image performance with a real NLP, NSF, and RGF with simple random sampling and RGF with non-hierarchical sampling. So the last column is the exact image. We can see that our RGFL performs better than the other baseline models. And the table also provides a quantitative resource for these examples, including 4 metrics. The higher, the better. Our RGFL can beat the baseline as well. Also, we test our methods on 2 real-world applications to demonstrate our effectiveness. The first one is MRI, which is a typical inverse problem given the known linear forward operator. So, for example, we can obtain a real measurement from some space and reconstruct the target images by solving inverse problems. In this work, we apply our RGFL method to quantify reconstruction uncertainties and error given different speed-up rates. There are 4, 6, and 8 times. So the left is the brain case and the right is the knee case. After training, we generated 1,000 samples from the learned posterior distribution and use these samples to estimate the means, the deviations, and errors. Compared with the straightforward methods, so our reconstruct images is more accurate and the standard deviation is much smaller. So the detail can be found from our paper. Under that, I will also provide a statistical summary of the posterior distribution on both MRI cases in terms of standard deviation, errors, and form metrics of the evaluation of general models. Our model also shows great performance in these metrics compared with the straightforward methods. Another example is the black hole image reconstruction. So the special frequency measurements have phase errors and noises, which lead to a non-convex, nonlinear image reconstruction, where a challenge is multimodal posterior distribution. In other words, the multimodal issue means there might be different solutions fit the same measurement data. So in this example, we use the data from EHG collaboration in 2019, and you will find more details from their GitHub. And our methods show good performance with smaller reconstruction error and uncertainties. And also, we observed and identified 2 different modes given a specific same measurement. So I think that's it.